Okay, so previously we talked about homotopies, more specifically path homotopies, in wherein we concluded that a thigh, a femboy thigh, is actually homotopic to two sticks, which we embed into the thigh. Using some inclusion map, or again, embedding, we say that these two sticks, I would call them S, ST, and this is the FT. Not to be confused with FT, which is torus. But just regular T would be an annulus, I believe. So, not to be confused, this is secretly, so ST, we just say ST is a subset of FT. But of course not equal to, so we add that small thing in the bottom with a tick mark. So we showed these to our home topic by sort of embedding it here, and then so right, if these are two sticks embedded into it, so now this becomes FE union ST. So we just grab every point around the boundary or along the boundary of the thigh, and then we map it to a special point. Map it to a special point on the stick. So it's a perfectly normal function. It's not weird. If these 2 points map onto the same point, that's fine because it's a many-to-one association. We can't really have a one-to-many because that would give us ambiguous outputs. But this is okay, this is allowed. This is generally allowed, so same thing here. I mean, if you want, it could be bijective, wherein, 2 points here along the boundary of the thigh doesn't exactly map to the same point, but two neighboring points. So when we say that there's a homotopy between these two points along the boundary of the thigh have a corresponding. So if I take a point, so I'll draw it again. So if I take a point over here, I'll call it rho. If I take a point rho along the boundary, which is it's an element along the boundary of FT, so the thigh. So if I take a point rho along the boundary of the thigh and apply this this homotopy, which is called R, because it's called a retraction after all. In the end, it's called a retraction. So there's okay, let me just clear this up a bit. So this sticks. So there's a map that takes this into that. So this is here. Sorry. Oh yeah, no, right. That's R. And R is a retraction or deformation retraction. So if I take a point here along the boundary of this this space, now this is technically a space already, or a manifold. It's continuous. There's no holes in it. Okay, if I take a point P and apply R, there is a corresponding neighborhood. If I take a neighborhood around P, right? If I take a neighborhood around rho, I mean. So let's call a neighborhood mu, which is a neighborhood of P. Or rho. If I apply R onto mu here, it's distinct. So each image of the neighborhood mu, so each image of every element in the mu, which is a neighborhood of rho, is distinct. So each, I would call image R rho I So I is the index set. In our mu is distinct. So we can restrict the homotopy to have this condition that if I take an interval over here, say this interval around P, and then apply R on that interval, there is a corresponding, each of these points are mapped onto separate points and not just one point. However, we can say that, of course, we can also say that all rho I can be mapped onto the original image, R of rho, which is along the stick. So there are one of two things that we can do with this homotopy. One, we can restrict every neighborhood here. We can restrict every neighborhood or force this R to be a bijection, or rather, it would be a one-to-one mapping really. Not really bijection, but maybe a surjection or an injection. We can force it to be an injection from here, the boundary, onto the sticks. And in such a way wherein every neighborhood here has a one-to-one mapping with its own neighborhood on the stick. So this neighborhood is mapped onto this neighborhood, with this point being R of rho, or the image of rho under R. All these are mapped onto their own separate points and not onto just one point. Though it would kind of be silly, it would be silly if we decide to map all of these points onto one point. However, we still need to fill in the gaps wherein we usually would want these points to go to. So because we forced the second condition, which is that all of these points in this neighborhood map onto one single point, the image of this map R, or this retraction, ends up becoming smaller than we anticipated, and it's not roughly the same length as the thigh, but that's what we want. We want this stick to be roughly the same size as the thigh, but at the same time, it's not precisely the same, but rather a skeleton. We can, if we want to project a human skin, if we just assume that a human body part is only a ring of flesh around, or a cylinder of flesh around another cylinder, which is the bone structure, a very thin cylinder, we can map all of those points onto that single cylinder, and we should get the same length. But because we mapped, or we forced the second condition on this mapping R, we end up with a skeleton that's shorter than the initial thigh, which we don't want. So really, what we should do is discount this condition here. So don't force this condition at all. It really has to be a surjection or an injection, wherein these neighboring points map onto the same, or map onto distinct images, which maintain the length of the sticks. So yeah, that's what I neglected to mention last time. We explored more on this homotopy. So now let's talk about cell complexes. So we've established femboys in a line. We have distinct fine lines of femboys, but that's really only scratching the surface of what we can do with these lines of femboys, or intervals of femboys. Because the primary way of constructing spaces, especially tori or spheres or real projective planes or things like that, topological objects, is through these things called cell complexes. So I already told you guys what the cell complex is in the last lecture, but I didn't dig deep into what we actually do with them. So Right, recall this here is the cell complex of Ft2. So if we construct or assume these are all congruent, actually this is best interpreted as a rectangle, but I'll make it a square for now because it doesn't matter. The length doesn't matter really. Okay, so if we say that these lines here are made out of femboys or made out of a fine line of femboys, then this, when we identify each edge to be the same edges, like so if we identify these two edges and then we close it into a cylinder and then identify these edges, right, so this becomes a cylinder wherein this here is A, and then this length here B identified with B, so it is B1 and B2. B1 is identified with B2, it's A1, A2. And then next, we identify A1 and A2 to be the same edge, and then we get a torus. When this over here, this ring of points is, not really ring, but rather structure of points along the vertical of it is A, one identified with A2, and then the entire length that runs along the horizontal is B1 identified with B2 to be the same one. So from our initial square of femboys, we get ourselves a torus by identifying each of these edges. So from here, from this some femboy interval F1 cross F2, we get something that's Ft2. So this square F1 cross F2 is homotopic, or well, it's homeomorphic to Ft2. So this is one example of us using these simple geometric polygons to construct a complex structure such as a torus. So yeah, there's a very pragmatic use for these things. After I introduce to you guys another one of these guys, I will show you guys the formal way of constructing these cell complexes. So how do we actually make this rather than just drawing it and illustrating what the parts are and what the relations between those parts are. So we will make a formal definition of this based on algebraic topology. So the second example is an octagon. So if I take an octagon and identify various parts of it, we get a genus 2 surface. Where the genus 2 surface is a space with 2 holes in it. So again, let's think of this octagon as a fine line of femboys. 2, 3, 4, 5, 6, 7, 8. And then this, that, this, that. I'm guessing this goes here, and then this goes there. And I know it's a bit messy, and indeed, when you try to identify these edges, it would be better if you use a computer to identify them. And then B, and then A, C right there, C, and then A. This is A. Okay, so you guys can start with B, identify those two guys together, or start with C. Start with C, identify these two guys together, and then we get some portion of this thing. So I'll just draw the full picture. So we get a two genus surface, so a surface with two holes. And if we allow this part here, this vertex, to be our center point, the center point, which is the vertex here, once we're done identifying it, we get something like this. So just that way, like that, and then it closes back. And then this is the two A edges identified together, and the entire length that runs through like that is all B sides identified together. The same thing here mirrors, but except it's C this time. So C, this is C, and then that runs along the vertical of that part is D. So this is homomorphic to that. Under the identification stuff where we attach them together. So you'll notice that this is a more complex space of femboys now. So this is one way of showing, okay, if I have a fine line of femboys, I can construct a gigantic space of them that's probably bigger than its constituents by gluing these guys together and saying, okay, these line of femboys are practically the same line of as these femboys via some equivalence relation. Okay. Now that I've showed you guys, what cell complexes are, or some examples of it at least, let's actually formally construct these guys. So before I start, I'm assuming you guys know what a disk is. A disk is basically the two-dimensional version of a ball, which is the enclosed, or we can think of a disk, dn, as equal to or homeomorphic to the closure or the interior of Sn union its boundary. So a flat disk is the inside of the inside and the boundary of a circle, S1. But I believe there's a more different definition. This is just the way how I like to think about it. Okay, so there are two ways we can construct cell complexes. So the first way, so this is formal now, a zero skeleton x0. So if x is our topological space, this x0, consisting of a discrete set of zero cells. So our notion of formalizing a square, that's the cell, the end cell. So the zero cell is just a point. So if we want to construct a cell complex of dimension 0, this is really what we are going to do. So that's why there's two separate cases, because we don't want to construct we don't want to say that, well, the second case wherein we do construct something that's non-zero dimensional is practical homotopic to this under the same condition. So that's why we make it a separate condition. Okay? So the second condition, or the second method of constructing it, is that inductively, we can construct it inductively with a period. Inductively. So given the K skeleton, so the skeleton is basically just that polygon that we're saying, which we identify to construct that space. Okay? So this time xk, k is non-zero. Form So we form now the k+1 skeleton. So we increase the dimensionality or the degrees of freedom. So if we primarily start with one dimension and with the line, we add a second perpendicular line of femboys to that one to obtain our k+1. If it's 2 this time, if we have 2 over here, 2 femboys, we add a third axis. Now I can't make it with my arms, but we make a third axis. And then we essentially have a cube of femboys. But that's only the skeleton of the entire structure. Okay. So by attaching k+1 cells, which we will call, form this by attaching k+1 cells, which I will call E alpha. Now this is not the identity. It's E alpha to the k+1. So really, the skeleton of the cell complex is our way of identifying them, I believe. And then so these are just the actual lines that we construct, right? So it's made from yeah. Okay. So the skeleton of our cell complex is, well, it could be thought of as a complex itself, such that we construct these cells to, into products of themselves or products of each other to make the actual structure of the object that we want to identify, the edges of. Okay, so attaching these k+1 cells, which we'll call E alpha to the k+1 through attaching maps. Through attaching maps, which we will call phi, that maps the boundary of the k+1 disk onto our skeleton, or k-skeleton xk. So we take the boundary of a disk, so basically just a circle of it, and then we embed it into xk. Or actually, we sort of retract it onto k. So because the boundary of this disk here is a dimension higher than this skeleton, this k-skeleton. So what we're essentially doing is retracting it onto here. And you see now why retraction is important here in algebraic topology. Because when we try to map this boundary onto this k, so this sort of circle string of femboys, or line of femboys, we're putting it into this here now. So we're putting them among a lower set of femboys, or femboys with less amount of qualities about them. So here we have more qualities, or we have more characteristics to describe a femboy. Here we have less characteristics to describe a femboy, and we're mapping each of these femboys along this disk, or along the boundary of this disk onto this lower dimension. So we're essentially losing some structure, but not all the structure. Okay, so such that x to the k+1 is equal to x to the k, disjoint union. So we're gluing it now, x to the k glued with respect to this map, or indexed map. Oh, sorry, this map is indexed. So there's a family of maps. And this is a homotopy. That's why it's a family of maps. Sorry, I totally forgot this alpha here. It's a family of maps, which is why it's a type of homotopy, which is essentially our retraction, the deformation retraction. So yeah, that makes sense. Okay. And then just index that. Okay, so d to the k+1 alpha. So we attach these index disks of femboys onto this entire space of femboys. So we still lose structure, but we sort of still kind of maintain some of the structure, but we just sort of glue it here. It's like gluing a sphere onto a plane, right? That's when we're interpreting it. Okay. And yeah, that's the end of it. So once we do this gluing, we get our C complex or our cell complex, which we use to identify each edge to get a certain specific space that we want. Yeah, my birds are pretty noisy. So, okay. Okay, now let's talk about path homotopy. So, you guys remember our discussion of paths in the last video. There are types of curves. They're continuous curves, basically. So, recall the definition. Let's kind of wait for my birds to settle down. Okay. So recall that the path on a space X is a map gamma from the interval 1 to 0 onto X. So now let's define path homotopy. So when we first were talking about homotopies, right? These are lines of femboys that we kind of think are the same. So now let's think of them in a more physical form, in the form of a path, and path homotopy. Two paths of femboys are path homotopic if they're homotopic relative to the endpoints. Or relative to the endpoints. I mean, we can say with respect, but reserved it for calculus. So if we have two paths, I'll call it gamma 1 and gamma 2, and we restrict them to the points 0 and 1, they should have the same image under that restriction. So the image of this here restricted to 0 is equal to the image of gamma 2 restricted to 0. And the image of gamma with restricted to 1 is the same as the image of gamma 2. Sorry, gamma 1. Gamma 2 restricted to 1. So they should have the same endpoints and stuff like that. So if this condition is met, then we say, or we say that gamma 1 and gamma 2 are path homotopic, and that's denoted by this homotopy, and then just add a p right at the end of that. So gamma 1 is path homotopic to gamma 2. Because if we say full homotopic, this condition is not necessary here. Because homotopy is a very loose definition when it comes to curves, right? That when we index this thing, right? When we index this thing into a family, one input from it would be corresponding to some, with a corresponding indexed output. But here, we're saying that these two have the same outputs at the endpoints, essentially have the same output, right? Or outputs at both endpoints which are homotopic to each other, or at least homeomorphic if it's a higher dimensional space than 1. So we can think of this as, I have a point here, or a femboy here, and a femboy there, and this here is gamma 1, and then this here is gamma 2. Same thing. They're practically the same thing, or they're path homotopic because they end up, or they run from the same starting point and end at the same ending point. So, path homotopic, path homotopy. So, okay, because we're modeling F, or the space of all femboys, after R, here's an important fact. So this is a sort of recursive theorem, or yeah, that requires a recursive proof. So theorem. Let F be a subset of big F, or math F. So it's a subset of femboys, a collection of femboys from the space of all femboys, right? Fn, sorry, Fn. Two maps, which I will call gamma 1, gamma 2. No, it's not called gamma. It's called alpha. Not index, so I don't need to use alpha here to index it. So alpha 1, alpha 2. So two maps, alpha 1, alpha 2, that maps 0, 1 onto this subset. So we assign a number for every femboy here, so it's like a listing, right? But at the same time, this is described as a path of femboys, or a line of femboys, a fine line. So these two are path homotopic. Are path homotopic if and only if they have the same endpoints. And the proof for this is just use the definition. And that is by indeed, under this definition, it holds that some alpha 1 of 0 is equal to alpha 2 of 0. It's true that this holds, and I mean it holds that if we assume this to be true under the definition, it must be the alpha 1 of 1 is equal to alpha 2 of 1. And that, of course, because of that, it must be that if we assume this to be true, but we say that it's not really homotopic, then our definition fails, or our proof already fails. But our assumptions are already false, but we already know it's true in the first place, right? So indeed, if we let that be that, then Ft or Fi S, or actually alpha I of S. S is some input, okay, along the path. So S is an element along the path, or alpha I of S is some element along the path. Alpha I of S is equal to 1 minus I times alpha of S, alpha 1 of S, plus I alpha 2 of S. You guys can verify that on your own, and that's I'll leave that as an exercise. Okay. Now we've talked about paths. I believe it's high time. I believe it's high time that we talk about the fundamental group. Okay. So let's make another definition first before I actually define the fundamental group. Because another crucial invariant of these spaces that we study or that we will study here in algebraic Femboy theory is the fundamental group. Because when two spaces don't have the same fundamental group, they're not essentially categorized into the same category. So when we do construct a fundamental group of one space and then we construct a fundamental group of another space, if those fundamental groups are not the same, these two are different. They're essentially already different spaces, even though we haven't even done anything to them, like embed paths and then determine if we shrink those paths, they'd be the same, or they can equally be shrunk. So like it's one way of determining if two sets of ties are exactly the same or not really the same, or not at all the same by some preliminary, some abstract thing or invariant between these two. Okay, so let's make a definition. I will denote curly P of X our Femboy space. Is the path homotopy equivalence classes. Of paths in X. So every path that exists in X should surely be part of this, so long as they're homotopic to each other. And the reason why we call it an equivalence class, this is actually a class of functions or maps. The reason why we call it equivalence class is because homotopy is essentially an equivalence relation. So it makes sense to call this an equivalence class because we're talking about a collection of homotopic paths. And homotopy is essentially equivalence relation, so it makes sense to call it this. Yeah. So this proposition, this definition makes sense because path homotopy is an equivalence relation. Okay, so now let's move on to, actually let's make a lemma before we, I know this lemma would be important in proving something, and they reveal some important algebraic facts about members of this class. So, lemma. So the first one, there's actually a list, it's a list of lemmas actually. 5 lemmas, or 5 sub-lemmas under this one lemma. Let bracket F, or alpha, I'll call it alpha. Alpha bracket be an element of P of X. Curly P of X. let alpha element of curly P of X be a representative. Be a representative of curly P of X. So think of this as an, alpha I, which is an index for a representation for every single, representation for every single thing in here, and essentially just a representation of this entire class. Okay. So alpha. Can you guys see it here? Oh yeah. Okay. Alpha of 1 and alpha of 0 are, you guys can't see it anymore, are well defined. Okay? Now I'm not going to prove this lemma anymore. I'm just going to leave it to you guys to prove this lemma. Okay? 2. So 2 representations in here, so I'll call it alpha and beta. Alpha and beta in curly P of X. So if we let these things be representations, right? F of 1 or alpha of 1 is equal to, or is equal to beta of 0. So this is a loop. So the endpoint of this curve, or this path, is the same as the starting point of this path. Or they can be connected paths. So if this is path A, or if my arm here is path A, you can have a path B that starts at my armpit or the start of my arm, right? So alpha of 1. So this is equal to, okay. Yeah, so this is the visualization of it. I mean, you can also think of it as a loop, but yeah, think of it as connected paths. Okay, so given this, the composition, so I'll so let's call the composition of it, of these two, a concatenation. So the concatenation of alpha and beta is just alpha times beta. Right? So that's a concatenation. And we've played with concatenation before in my FEM lectures on proving that A comes before B. Right? And also, all throughout position theory, we've played with concatenation, especially string concatenation. Especially when, defining location and stuff. And even earlier in Femboy theory, we played a little bit with concatenation because of REL, which is the space of all characteristics of a relationship. Which, wherein it's best described as words, right? As literal words from the English language that describe relationships, like single, poly, stuff like that. And we play with string concatenation there. So this shouldn't be as difficult to understand. Okay. So their concatenation, or the concatenation of their respective representations of the entire thing. So concatenation of representation A times representation beta. So we can think of beta as some alternative representative of P of X. So this is just equal to, or this operation, which results in alpha, or the representation of alpha times beta. So a new representative of P, which is essentially alpha times beta. So apply beta first, and then alpha. So, and also we attach them. So that's the reason why we sort of associate them here, because we attach them. So this is well defined. Yeah. So that's the second one, second sublemma. The third sublemma is that, okay, so I have a third one now, a third curve that we can possibly represent. So it's an associativity that we're proving here. So we're showing alpha times beta, and then some new one which I will call omega, or a small omega, not big omega, is equal to the representation alpha times, this time we make the stuff here. We concatenate these two first. Concatenate representative beta and representative omega. So this operation is well defined. The fourth condition okay, is that okay? So now we have some curve, right? Okay, I'm gonna have to recheck with the fourth definition. So okay, f or alpha, so representative alpha multiplied by some, I believe some homotopy or some map. It's a map. It could be any map. It could be a homotopy. It could be curve evaluated at alpha of 1. So this is also representative curve is equal to some f or alpha. Sorry, alpha. Oh, so this is an identity operation. So concatenate this with this function here, and then we get just alpha, representative alpha. And also so this is only a right multiplication, a right concatenation, but the left concatenation requires that this be evaluated at alpha 0. So gamma alpha 0 concatenated with the representative alpha is also equal to representative alpha. And the last condition, so another thing I need to note above here, is that I forgot to list this definition a while ago, but if alpha is a curve, alpha bar, oops, I wrote too high. Alpha bar is equal to just alpha of 1 minus s. S is an input of alpha, or S is part of the domain of alpha, or the codomain of alpha. And so S here, just S itself is just the pre-image of every image under alpha. So alpha bar is equal to this. So that's the inverse. Now we can denote this alpha to the -1, but I think it's more convenient to just use alpha bar. Okay, so alpha bar, whether alpha concatenated with its inverse or the representative, its inverse becoming a representative, is equal to this map here. So gamma of alpha of 0. Gamma sub alpha 0. Okay. And so this is for right multiplication of the inverse. For the left multiplication or left concatenation of the inverse, we will get gamma of alpha of 1. Makes sense? And so that's the fifth one. There is. So this is the entire lemma. Again, I'm not going to prove it and stuff. Alpha bar is just the inverse of alpha, which we define to be alpha of 1 minus s. So yeah. And this gamma here is some identity function, such that when we concatenate it with alpha, we get alpha. I mean, if we take its input or it evaluated at alpha of 1 and then concatenated with alpha, we get alpha. And that's for a right concatenation. For a left concatenation, this is the condition here. This is what happens. The thing is, concatenation doesn't work the same way as multiplication or string concatenation. Especially string concatenation, because string concatenation employs some notion of order. Like two elements put together are not really the same. So AB is not the same as BA, right? Unlike multiplication, multiplication is commutative because 1 times 2 is equal to 2 times 1, which is equal to 2, right? So yeah, that's what happens. So a curve of femboys, line of femboys here applied with this this identity curve here, or concatenated with this identity curve, just gives us this. And you notice that this is actually just 1 or 0, just a point. This curve evaluated at a point, or this map at a point at A1 or alpha 1 and alpha 0 are simply just points. And it makes sense that when we add this, or when we include this into alpha, or compose them together, we just get alpha. That makes sense. And then likewise, when we add alpha 0 or gamma alpha 0 to this, we are essentially just adding to the other point, or other side of alpha, or at the starting point of alpha. And so we just get alpha because we're just essentially attaching a point to alpha, and that is negligible in the length of alpha. Okay? So we can think of alpha here, or this bracket alpha, as like a model femboys, or ideal femboys, or yeah. It's arbitrary, as all definitions here go, because of course trying to talk about femboys is arbitrary in itself, and that we are humans and humans are diverse. So there's no one singular model here, that singular alpha that can represent the whole. It's arbitrary, and that's why we really just call it alpha, and not alpha defined as a map and then explicitly defined function, because yeah. Okay, now that we've defined all this, let's actually go to the meat of this lecture and talk about the fundamental group. So it's high time for me to take lunch because I'm hungry. But I won't let that get in the way of my lecture. Okay. Just erase all this. Okay, so definition. So for each femboy, Fi, subset of normal big F, or let's call it Q or A. Subset of the entire space of femboys. Q, Fi of Q. Let, so Q is a space, okay, space of femboys. Let pi 1 of Q at the point, or at all these femboys. Oh no, sorry, this is F0. So let this be defined as the set of all representations F or alpha in Q, or in the curly of Q. Such that F of 0, or alpha of 0 is equal to alpha of 1 is equal to just F0. B, the fundamental group of Q at the femboys of Q with base point base Femboy F0. So the reason why we call a group is because this forms a group, or this set forms a group under string concatenation. Because you notice that if we concatenate this, or one of these guys, or one element of this entire set, you know, these things such that their endpoints, they're a loop, right? And then they're equal to some base point, or their loop is some base point, or starts at some base point. If you concatenate them, we get something that's the same thing, according to our previous lemma. Yeah. I mean, yeah. According to our previous lemma, these would be any concatenation between elements of this entire set would also be contained in this set. And so I suppose each of them would have their own inverse, and that it's not necessarily commutative, because a commutative group is some separate thing. It's called an abelian group, but that's something else. So we don't really care about commutativity here, and that concatenation of these curves or these paths would just be, you know, it would depend on left or right concatenation. So it forms a group under string concatenation. That's what we call a group. Now, P of Q, according to the lemma, P of Q is now called a groupoid. It's a groupoid. Now, if I recall, what the groupoid is. So P here, P of Q, forms a groupoid called the fundamental groupoid under the previous lemma that we listed. A groupoid is somewhat like a group, but not entirely a group. In a way, it's a group, but we don't necessarily require inverses. And you notice that alpha inverse is part of this. So each curve has its own inverse in PQ and in this set. So this qualifies as a group. And of course, you saw from a while ago that operations here, or concatenations of certain curves here, or certain paths here, yields something that's inside here as well. So group also. So and also we saw the associativity, which is important for group. So it really proves that this is a group. Under concatenation, of course. This thing here is just a set, but equip it with concatenation and you get it. You get this. So I didn't formally define it, but concatenation is an n-ary group, or n-ary operation that takes multiple inputs and then takes them into the same space. It's an n-ary group, or n-ary group. I mean n-ary operation, or n-ary relation. Not really binary, trinary, because we don't only take 3 outputs. We can take multiple concatenations. So, if any 2 points can be joined by a path, or if for short we say that Q is path connected. So if any 2 femboys can be connected with some line, right, or line of femboys, other femboys. So if we make one femboy line up a bunch of other femboys that ends up to another femboy, right? Then, or say that Q is path connected, right? Then this fundamental group at base point or base femboy F0 is independent of that base point up to an isomorphism. So I already defined what an isomorphism is. It's a mapping between groups and stuff like that. So up to some identity morphism that takes this exactly to another group. There is a, of course, yeah. If that's the case, if Q is path connected, then this is just regularly, if Q is path connected, so if Q is path connected, the fundamental group of Q, base femboy 0 is independent of that base femboy. Okay, up to an isomorphism. Isomorph. And it is so often called, or often denoted, just pi 1 of Q, or pi 1Q. So just straight concatenate pi 1 and then Q together, or remove that base point if Q is path connected and thus independent of the base family. So that's that. So more on the fundamental group. So a couple more things about the fundamental group that we're going to talk about before I end this lecture. So this now is the fundamental group. So we think of a space and then all paths in it. So a space of femboys, a gigantic group of femboys, not really group, but rather a space of femboys, and then a bunch of lines of femboys inside, specific lines of them, and from there on, or a collection of those lines of femboys, and then we construct some variant or invariant of them, or set of all of them that satisfies some conditions such that they're loops, right? And this is what I was talking about in the previous lecture, about determining if two spaces are the same. If they have the same femboy, the same fundamental group, we have a loop inside them that we can shrink without it stopping. So, essentially, if I have a torus, right, it has a hole in it. Even though I can make a loop in it that we can infinitely shrink, there is one loop. There is going to be one loop such that when we try to shrink it, like how we shrink a loop on a sphere, right? So we're first determining if Fs2 is the same as Ft2. Of course, we're saying that no, they're not the same, but we can construct one from the other. So Fs2 and Ft2 are not the same, or Fb3 is not the same as Ft2. Right, this is what I was talking about. That if they have different fundamental groups, then one of them has a loop that we cannot shrink, or at least they have at least one loop or one path of femboys that circle on into a loop that we cannot shrink. So if we make those femboys move closer to the center of or the centroid of their path, they can't do it in one of those surfaces if their fundamental group is different. Or if the fundamental group is the same, either we can shrink those femboys infinitely as much as we want, or we can shrink those loop of femboys infinitely as much as we want, or we can't do it in both of them. So either we can in both or can't in both. And those are the two conditions that happens when both of them have the same fundamental group. But if one of them has a different fundamental group, then it's either only one of them we can shrink those loop of femboys infinitely small, and the other we can't. Okay. So more depths on the fundamental group. So a fundamental group, I'll call it star 1, fundamental group of some Q at base femboy 0 is similarly defined. Or I'm gonna say that this is sort of equivalent under or implies or is somewhat the same under some maybe some homotopy or isomorphism as the map F that maps the interval 0, 1, K onto Q. So we're saying that this is somewhat the same, or can be described as a, of course, F that maps multiple K cells onto the space. So multiple, intervals of femboys onto Q, or multiple inputs from those guys. So actually, we can either think of this as, one single entity, right? And we're mapping that one entity, or taking that one entity onto this space, either as an inclusion or losing some structure, or endowing of coordinates, or description, way of describing, or characteristics. Or we can think of these as, we're taking one femboy from this interval k amount of times, or distinct femboys from this k amount of times. So this takes the femboys f1 fk, and then taking them onto some image f of f1 fk. Actually, I'm going to know as a row so that it doesn't confuse it. You don't confuse it with the femboys. So this time is a map. So it takes it onto row of these, which is a subset or an element. It's a collection of these things, so it's an element of Q, or subset of Q. Unless it's open, where it's an element of Q. Okay, yeah. So it's either this or the entire structure, or 0, 1 times times 0, 1. And this is k amount of times. Or rather, we can think of this as a product. I equals 1 to k of fi. Or, 0, 1. Is taken. Is either injected into Q, or included into Q, or this product is just taken to Q, or mapped to Q. Mapped onto some subset A of Q. Okay, so these are the two interpretations we have, or at least three, of this map. But I believe it's the first one. It's the most plausible. Okay, the second one, second star, the base point, in our case base femboy, doesn't matter. So no matter what base femboy I pick, it doesn't matter which one I pick. Because every path between 2 points induces an isomorphism between the respective fundamental groups. Every path induces an isomorphism. Every path between 2 points induces an isomorphism between you add f0 to I1 of Q and F1. So what I'm saying is, if we change our base point to F0 to F1, every path that connects those two, right? If we make fundamental groups of each other, we can always take one fundamental group to the other. So there's an isomorphism between these two guys. So they're sort of equivalent in a sense. So now, the last one is that a convex set of femboys, which I will, of course, call Q again, which is an element of big F, or mathcal F, has the trivial fundamental group. which is pi of x, q, at a base Femboy 0 is equal to 0. So a convex set is basically any shape that you can think of such that any 2 points on the boundary of it, two antipodal points, or points on the boundary, is contained entirely in this set. So if I make a line that connects 2 points on the boundary of a convex set, the line is contained entirely in the set. So really no holes or bulging inwards. So this kind of space is not convex, because if I connect these 2 points here, you notice that this section of the line, this small section over here, is outside the set. But something like a ball or a sphere is convex, because notice if I'll put 2 points here, the line is still inside the set. And then here, line is still inside the set. Here, here, line is still inside the set. So that's convex. This is concave. That's an ingenious way of defining convexity, actually. I love that definition. And it's a very powerful one at that too. So that's the last thing here for today's lecture. So I know this has been a very long lecture. It's been 1 hour already. So please time to absorb this. So I guess this is it for this lecture. We're in the middle of restructuring the entire curriculum here at LOSC. It's just that we looked at other universities and realized, oh, we've been doing it all wrong. So we decided to scrap a bunch of other courses and only decide to list down the courses that we teach thus far. Of course, this is part, and they're all categorized under major categories such as physics, math, core studies, or just QST. Of course, there's also med or medicine, but we're not really gonna go much into that. So this is the second lecture, and so this is a good place to stop.